Thank you. And the next presenter will be Amber Parf, who. So first, thank you for. I see you have been attending almost the whole workshop. Thank you for that. So Amber has been a PhD student of computer science at Johns Hopkins University, working with Professor René Vidal, and he has done very interesting work recently on using understanding deep network and mostly adversarial attack and defense, which will be today's talk's theme. So please go ahead, Amber.
Thanks for the introduction, Atlas. Right, so as Atlas said, today I'll be talking about our work on understanding adversarial attacks and defenses from a game theoretic perspective. This is work with my advisor, René Vidal. Okay. Right. So as a background, recently the field has seen this insurgence of adversarial attacks and defenses on neural network classifiers. So additive adversarial attacks is a specific class of those attacks in which, let's say you have an image of a dog on the top panel, you add a small perturbation, which is the adversarial perturbation, and the neural network now classifies the resultant image as a cat. In response to these adversarial attacks, people have proposed defenses. A particular class of those defenses is pre-processing defenses, in which you take the image, the perturbed image, and then you apply some correction algorithm in order to get a corrected image that is hopefully classified correctly as with the classifier. Okay, so this has been going on in the literature for a while, and what has really happened is that in the literature we have seen a cat and mouse game between these attackers and these defenders, in the sense that first of all, these attacks were proposed that broke existing classifiers. And then people came in and they proposed new defenses to these attacks. And then just the next year, all these defenses were again broken by new attacks that were proposed in the next conference. So this cycle's been going on. And in this work, we start with the motivation that in this cat and mouse game, the attackers always seem to win, sort of. So we ask if there is a level playing field. And whether we can analyze these adversarial attacks and defenses in a sort of fair framework to both the attackers and the defenders. And so we propose this following three-step framework to have a fair playing field for analyzing attacks and defenses. So the first step is to precisely specify the attackers and the defenders' knowledge. So specifically, we will work with saying that the attacker knows all possible defense strategies. So if I'm an attacker, I know all the possible strategies that you can use as a defender. These might include making some modification to the first 3 pixels of the image, or recolorizing the image, and so on. Similarly, as a defender, I would know all the strategies the attacker can possibly use to attack the image. However, none of them knows the exact perturbation or the exact element of that strategy set that would be used at test time. Secondly, we will assume that the attacker and the defender submit their attacks or defenses, in this case, image modifications, simultaneously to the test point. And thirdly, we will have a score on misclassification. So we'll give a +1 score to the attacker if the resultant image after the attack and the defense is applied to the image is misclassified by the classifier. And we'll give a -1 score to the defender, and vice versa. If the image is not classified incorrectly, then we give a -1 to the attacker and +1 to the defender. Okay. So just to set up the problem a little bit more, we are looking at this test point X here, and the attacker is allowed to add additive bounded perturbations to this test point X. So everything inside the red ball is fair game. The attacker also knows everything in the green ball. So by that, I mean that when I make the perturbation that is made by this red arrow here, I know that the set of all possible perturbations that my defender can make lies in this green ball. As an attacker, I also know the blue decision boundary. This is a linearized decision boundary right now, but it can be more complicated. And finally, I get a +1 score for misclassification. So if the final perturbed X is misclassified by the blue classifier, then I get a +1 score. Similarly, from the defender side, again, I can add, as a defender, I can add perturbations in this green ball. So that is, you see mentioned as V subscript D here. And I know the possible attacker's perturbations. So I know that the point I'm currently at might have come from applying some red perturbation to X, but I don't know which one. And again, I know the decision boundaries of the neural network. So that's the blue decision boundary here. And I get a +1 score for correct classification. So if after I apply my defense, the point X gets classified correctly, I get a +1 score. What I have described in the previous two slides is basically a two-player zero-sum game. So the two players are the attacker and the defender. The zero-sum comes from the fact that whenever the attacker gets +1, the defender gets -1 and vice versa. And so with this setup, the main theoretical question that we will ask is that, can we find an optimal attack and defense pair where optimality is defined by saying that the attacker cannot improve the score when the defender is fixed, and vice versa, the defender cannot improve the score when the attacker is fixed. In a sense, what I'm trying to say is that I'm looking at this cat and mouse game where attacks are proposed, defenses fix these attacks, new attacks are proposed, new defenses are proposed, and so on. And I want to find this attack star and defense star, which are optimal in some sense to each other. So if I play defense star, then you cannot do better than attack star. And if you play attack star, I cannot do better than defense star. Okay. This setting is precisely a good setting for using ideas from game theory, where this above situation is called a Nash equilibrium in game-theoretic jargon. And additionally, we will also note that my attack and defense algorithms can be deterministic or they can be randomized. Okay, so our goal now would be to find these Nash equilibria in this particular setting to get a pair of optimal attack and defense for a specific class of neural networks. Now we'll define that particular class of neural networks and the attacker and the defense strategy families that we will be working with. So we'll have the following restrictions on the defender. The defender would be restricted to follow an identical strategy for each input, which is to say that, let's say there are these 3 points, x1, x2, and x3. And as a defender, I want to make one additive perturbation to these 3 points. Then I can make any of the green perturbations, but the distribution of over the green perturbations needs to be the same for all the points. Okay. This is basically modeling a large number of existing defenses in literature, where let's say you go to every point and you smooth the point a little bit by a Gaussian blurring, or you recolor every point by the same recoloring function and so on. So the strategy is identical for each input, but the strategy can be randomized. The second thing that we assume is locally linear decision boundary. So we assume that the decision boundary, that was the blue decision boundary that we saw earlier, it is linear in a small ball around each input point. Okay. And this ball, by the way, is pretty small. It's equal to twice the size of the maximum allowed perturbation. That's typically the epsilon you see in these adversarial attack papers. So specifically, the decision boundary can be given by this green, by this black curve. But inside the ball, the decision boundary is linear, as you can see here. So those are the assumptions that we will work with. So under these assumptions, we will show our main result, which shows that the fast gradient method attack and a particular randomized smoothing defense form a Nash equilibrium. Okay. Again, the implication is that if I am using fast gradient method attack, then the defender cannot do better than randomized smoothing, and vice versa. I'll go into the details of what is randomized smoothing and what is fast gradient method in just a moment. But that is the main result that we have in the paper. Of course, it comes with some caveats. The caveats are that, as I mentioned, the results are for local linear decision boundaries, and we have norm-boundary perturbations. So perhaps the second one is more standard. The first one is not that standard. We have some explanations as to why is this local linear decision boundary assumption a good assumption. And in fact, people have been using this local linear decision boundary assumptions to improve robustness. There are papers showing that if you promote local linear decision boundaries by some training tricks, then you actually improve robustness. The second caveat, which is probably will make sense if you are familiar with randomized smoothing, is that I am smoothing here with a distribution that has a bounded support. So it is not the general randomized smoothing with Gaussian smoothing that is generally seen in the literature. And the third caveat is that I need access to the full generating distribution Px in order to find this optimal randomized smoothing defense. So the remaining results in the paper basically deal with fixing this last caveat. Um, so let me first of all give a very super short overview of randomized smoothing. The randomized smoothing is basically a defense technique in which we start with noting that adversarial attacks take advantage of these crevices in the decision boundary. So let's say your F is your classifier, then you might have this small crevice in the decision boundary that makes your input X be susceptible to a red adversarial perturbation that makes it go to the which is X prime is close to X, but is still in the other yellow class. So the idea behind smoothing is that you improve adversarial robustness by making these classifier boundaries smoother. Okay. So you want to take this F and you want to transform this to a G that has much smoother decision boundaries. How this is typically implemented is that you take every X, and what this G does is that it produces several of these noise perturbed copies of X and finds a prediction of F on each of these copies, and then take the majority of these predicted classes to obtain a final classification. It can be shown that these three steps, if you perform these three steps to get G from F, you actually end up smoothing these decision boundaries. And that also leads to other certificates on the robustness of this G that you obtain, right? So going back to our setting now, what we require for our setting is randomized smoothing, but with bounded perturbations. So we will not be doing this Gaussian smoothing now, but we will be smoothing a small ball around X. And so the main difference is that we're smoothing the bounded perturbations, which basically means that we are perturbing X by several norm-bounded noise. And the point in the previous slide here was that we need access to the full data generating distribution Px in order to find the set over which we'll perform randomized smoothing. So we'll need a subset of directions on which we'll perform randomized smoothing. And we need the full data generating distribution Px in order to access this set. So the next result basically shows that this optimal attack and this optimal defense can be approximated given finitely many samples from your training data and the model, obviously. So the attack remains the same, that is the fast period method, whereas the defense can be approximated given finitely many samples from your training data. And finally, we show that this particular approximation, this gets better at a very fast rate as the size of the number of training points you are allowed to access increases. So the rate at which it gets close to the optimal defense is something like log n over n. So it's very fast. And again, the attack remains the same, which is FGM, regardless of the number of samples. Okay. I'll conclude there. To conclude, the takeaway message is that we can formulate these attacks and defenses in a game theoretic framework, where for locally linear classifiers, this class of neural networks which are locally linear near your data points, the optimal attack is the very simple attack, which is the fast gradient method attack, and the optimal defense is an instance of randomized smoothing. It cannot be computed exactly, but it can be approximated. And this approximation enjoys nice convergence properties to the optimal defense. Thanks a lot for inviting me to the workshop. And you can find more details at our new tips poster, I think in 2 weeks.
Thank you, Amber. I definitely will need to read your paper in more detail, but just one question. So for the fast gradient descent, those fast attack method, I think in general, recent work find they suffer from catastrophic forgetting of adversarial robustness, like overfitting of the attacks. If you trend towards them, you will see the robustness accuracy first increase and then decrease. So how you see your method? I understand you say that your defense have modified random smoothing to a bounded perturbation, but could you share some insight how this fast gradient method could not provide a very sustained robustness and empirically show easy to overfit, and how that is relate to or be compatible with your theory here?
Right. So I think the main reason why the simple fast gradient method attack works here is just basically because we have a local linear addition boundary assumption. So that's why the attack turns out to be optimal.
So
With
okay, so that's the reason. I see. Okay.
right. With respect to your question on overfitting during adversarial training, the bound that we have here right now. So if you go back to the main theorem. So when you look at the main theorem, it also includes a characterization of the a precise score that the attacker and the defender gets at optimality. So and that score depends on the neural network's decision boundaries. So the score depends on how the decision boundaries are with respect to the individual data points. As a byproduct of this theorem, you also get a lower bound on the uh, worst defense performance, or vice versa, and then upper bound on the uh, best you can do using defense. So it sort of gives two bounds as a result of this game theoretic analysis.
No, just sorry, just make sure I understand. So, for your equilibrium, is that a stable equilibrium? Like, if I slip away from this stationary point, is it easy for me to go back, or it actually could catastrophically broke?
Right. So there are infinitely many equilibria, precisely because of the set which you are randomized, over which you are performing randomized smoothing, that has an infinite number of sets you can do this randomized smoothing over.
Yeah,
Whether this is a stable equilibrium or not, that I little to think about, because it is yeah, there is there is no sense of dynamics here though. So it actually might well be possible that if I am at this equilibrium, then nearly everybody around me has a higher loss than me. But I need to think more about that. I cannot tell that to you off the top of my head.
I see. Yeah, I also need to read your paper in more detail, but thank you very much for this very nice work.
Right.
And I will perhaps stop by your post next week too. Okay, thank you.